I checked.
All those other ideas are applying to the same. One is hard to the same.
Okay, let's get started with class for today. So today it's going to be one of those, it's Friday, so the first half is going to be me going over lecture notes, and then the second half is going to be a quiz. So the quiz is mostly going to be over projection, like it's mostly over section 4.2. Does anyone need the notes? Yeah, so we're finishing up chapter 4. We're doing section 4.4. We're looking at orthonormal bases, and then today we'll do an example where we use the Gram-Schmidt method to take a basis and then write it in terms of orthonormal vectors instead, which has a lot of applications that are useful. And so what we were looking at before, like on Wednesday's class, is we had n vectors, q1 to qn, that were orthonormal, and then we constructed a matrix out of them. And then with this matrix, the important property of this matrix is that it was an orthogonal matrix, meaning that if you took the transpose of this matrix, it ends up being equal to the inverse, which is a really nice property. And so we looked at one such example. This is what's called the rotation matrix Q, which is formed by these vectors right here. So you should be thinking this vector is kind of like polar coordinates from Calc 1, except it's going to be a unit circle instead of a circle of radius r. And then the second vector here, it's doing the same thing. It looks a little bit different, but I'll say something about it here later on. So this is a really important matrix. It'll show up later in this class as well. But the effect that it has, or how to think about this, is that if you do multiplication by Q on any vector, say like the basis vectors of R2, what it's effectively doing is it's taking the point 1, 0 on R2, and then it's going to be rotating it clockwise or counterclockwise along the unit circle. So you'd have like cosine theta. This would be sine theta. And then if you were to multiply the vector 0, 1 by Q, it would just be the second column. So it'd be this vector V2, which is going to be minus sine theta, cosine theta, which is still just rotating your point counterclockwise along the unit circle, except you're starting at the point 0, 1. So if you plugged in theta is equal to 0 here, you'll get 0, 1. If you plugged in pi over 2, you'll get minus 1, 0, and then so on and so forth. So even though it looks different, it just means you're rotating along the unit circle counterclockwise. It's really what this effect is. So that's why it's called the rotation matrix. It's just rotating your point counterclockwise along the unit circle. And so we talked a little bit about permutation matrices. We saw permutation matrices are orthogonal matrices in the sense that if you take the transpose of any permutation matrix and you multiply it by your original matrix, it ends up being equal to I. And so, for instance, if you're given a permutation matrix P, and then you define vectors that are just the columns of the matrix, then you end up getting vectors that are going to be orthonormal. So these are vectors that have a unit length and are going to be orthogonal to one another. These are orthonormal. And so this proposition, I think it shows up again in chapter 6. It's a really quick proof, so we may as well go through it. So this proposition, it wants you to show that if Q is an orthogonal n by n matrix, then the magnitude of the vector Q times x ends up being equal to the magnitude of x. So what it's saying is that when you apply an orthogonal matrix to a vector, it preserves the length of the vector. It's what's called an isometry, right? Because this is a invertible matrix. It's what's called like an isomorphism. So it's what's called an isometry. You can multiply by Q and it doesn't change the length at all. And so this is a common trick. We've done it a couple of times already, but we're going to do something like this. We're going to start off by looking at the magnitude of Q times x. And just like calculus 3, or I don't know, maybe professors do things differently than I do in calculus 3. They probably do, but usually when you're looking at magnitudes, you want to think in terms of like the square. So that way you can introduce the dot product without having to think about the square root at all. So we're going to look at the magnitude of qx squared. And we know this could be expressed as the dot product of qx with itself, which you can write as the following matrix product. So this is really the same thing as qx transposed times with qx. right? Again, this is really just the same thing as saying this is the dot product. It's just a different way of writing out the dot product. Just to make it clear, putting it into words. And so what we do here is we make use of the fact that the transpose switches the order of the matrix product. So you can write this out as being equal to X transpose times Q transpose times Q times X. And then you can make use of the fact that Q is an orthogonal matrix, right? Because Q is orthogonal, we know that Q transpose is equal to the inverse of Q. So if you multiply these two matrices together, you end up just getting the identity. So this is equal to X transposed times the identity matrix times X. Identity matrix doesn't change anything. So this is the same thing as just doing X transposed times X, which is really the dot product of X with itself. So this is equal to the magnitude of X squared. And so now if you take the square root of both sides, again, this is a number that's greater than or equal to 0. This is greater than or equal to 0. So you can take the square root, you won't have any issues. So upon taking the square root, you end up getting that the magnitude of Q times X is equal to the magnitude of X, which is what we wanted to prove. All right, so this is one of the benefits of writing the dot product out in terms of the transpose, is that we know how to do things with respect to the transpose. Like we know it has this algebraic property, and then we know that Q is orthogonal. So we know that the transpose has really nice properties as well. That's why there's kind of this this value in writing things out in terms of the transpose instead of just writing out as a dot product. Any questions about this one? Okay, so that's one idea. It will show up in the future, maybe like a month or so, or a couple of weeks from now. Really, the big idea from this section is outlined on this page right here, namely in the Gram-Schmidt process. On the third exam, there's going to be a problem where you're going to have to use the Gram-Schmidt process. So you have to understand how to do it. Otherwise, you're going to be out 10 points. And so why do we care about, I guess we've been talking about orthonormal vectors. My question would be like, why do we care about orthonormal vectors? And we've already seen some reasons, and that the matrices that you form from them have really nice properties. But we've also been looking at projection. So it'd be nice to say something about like projection with orthonormal vectors. And so these orthonormal vectors are going to be very convenient for projection. And so we're going to assume that we have k vectors, q1 up until k, qq, I can't say it for some reason, qk in Rn. So we're assuming that you don't necessarily have that k is equal to n. So you might have like a matrix formed by these vectors that aren't square. We're going to assume that they're orthonormal, and we're going to form a matrix Q out of them. Again, this means that you have Q columns, and then you have n rows. They're in Rn. And so we have that the projection onto the subspace spanned by Q1 to Qk is going to be the same as the projection onto the column space of Q. And so we use this formula that we introduced in section 4.2, except instead of A, we're using this orthogonal matrix Q. And so we get this projection matrix. And then we can make use of the fact that like these vectors are orthonormal, right? Because these vectors are orthonormal, it means that Q, the transpose of Q and Q itself is just going to multiply into the identity. And so these terms cancel out with one another, or I should say they become the identity. And so the projection ends up just being Q times Q transpose. And again, if Q is a square matrix, then this too is just going to be equal to the identity, which would then mean that the projection is just equal to the identity, which makes sense because if Q is invertible, it means the column space is going to be the entire space itself. So it means that everything's in the column space, so you can't really like come up with an approximation for what's in the column space is the idea here. And so I would ignore this line right here. This line, I don't think it really helps with understanding. It's just a different way of thinking about what this product is going to be or what this projection is going to be. The main point is projection with orthonormal vectors ends up giving you that the projection matrix is just going to be Q times Q transpose, which means that you don't have to go through this process, which is usually the part that takes a long time for these problems. right? And so that's what I'm getting at. Like projection with orthonormal vectors is very nice. It reduces the amount of computation you have to do very considerably. And so because projection with orthonormal vectors is so convenient, it's going to be worth replacing a non-orthonormal basis for any space by an orthonormal basis instead. And so this is what the Gram-Schmidt process is going to do. So with the Gram-Schmidt process, we're going to be given a basis. This is some arbitrary basis of your space, say like V1 to VK. And we're going to replace this basis with vectors that are orthonormal. And so the first step is you take these vectors and you replace them with vectors E1 up until VK, where all these vectors are going to be orthogonal to one another. So that means their dot products are pairwise equal to 0. And then we're going to make it so each of these vectors are going to be unit vectors. So you take EJ and then you divide by the magnitude, and that's going to give you QJ. And so when you're done with this process, you're going to have an orthonormal basis and thus make life easier for yourself. And so we need to go into more detail about how these EI vectors are going to be constructed. And really, that's going to be the hard part of this process. That's where you're going to have to use projection over and over again. And so this is the Gram-Schmidt process. It's I mean, maybe it looks worse than it actually is. It looks like there's like a lot of formulas, but really the meat of it, it's really in this part, or really it's this step right here. And so the Gram-Schmidt process for finding independent or 4 independent vectors V1 to Vn to replace them with orthonormal vectors is as follows. So how you begin is you just let E1, i.e. like the first of these vectors of your orthogonal basis, you just let it be equal to V1, completely unchanged. And then the next step is going to be constructing E2. So E2 relies on E1 in the sense that the dot product of these two vectors has to be equal to 0. So you need E2 to be orthogonal to E1. And so the idea is to compute E2, we construct the error between V2 and its projection onto E1. So we define E2 to be the following difference. And so it goes back to some of the pictures that we were looking at in section 4.2. So this exact picture was drawn in 4.2 before. So this is section 4.2, where you kind of have this picture that's going on. You have some vector V2, and then you consider its projection. So this vector here, this was our vector P. This was equal to E1 transposed dotted with V2 divided by E1 transposed dotted with E1. And then you have E1 here. And so our goal is we want to make it so we have a vector that's orthogonal to this vector here. And so that's the error. Really, it's going to be the difference between these two vectors. So if you were to bisect, or if you were to drop down the head of this vector so it intersects this one at a right angle, this is going to give you your vector E2, which is equal to V2 minus what I have written here in the quotient, which I probably don't have enough space, but maybe I'll try. So it's like E1 T V2 over E1 transpose times E1. So I'm just rewriting this over here. I don't have enough space. I'm just going to leave it like that. But that's where this is coming from, right? That's going to give you a vector that's orthogonal to what your E1 is going to be. So E1 is kind of the line. So this was the projection. I guess E1 is the vector that continues past the projection. But that's not really the important part. The projection is on the line determined by E1. Again, this is all from section 4.2. Like I'm not doing anything new here. And so that's how you get E2. And then for all the ensuing vectors like E3, E4, E5, you just repeat the formula over again, except you adjoin additional parts of the difference, right? So for V2, or to find E2, I should say, it was just this part. To find E3, it'd be up to here. And then if you're finding EJ, it goes all the way up to J minus 1. Another way of writing this out that, I don't know, depending on your level of understanding of summation notation, either makes it harder or easier to remember, is we're just saying that E sub J is equal to the following sum. It's going to be VJ minus the sum from I is equal to 1 to J minus 1. And then you do EI transposed times Vj divided by, it should be an I, EI transpose times with EI. And then you multiply by EI at the end. What I'm getting at is if you compare these terms with one another, the only thing that's changing is this E1 to E2 to EJ minus 1, which changes this to E2, this to E2, this to E2, so on and so forth. Like the only thing that's changing are these terms, the terms corresponding to E, right? So we're just doing this difference here. And so these are long problems. So on the exam and on the next example, I'm not going to ask you to do it like 5 times. That would be way too long. Usually on the exam, I'm just going to ask you to do it 3 times. So I'll give you like 3 vectors. You have to form an orthonormal basis like I'm going to do on the next problem. But once you get used to it, it really isn't that bad. It's just a matter of knowing this formula pretty much. Once you find all of the EIs, so the orthogonal basis, to make it orthonormal, you just divide all the vectors by their magnitude, and then you're done, right? After dividing everything by its magnitude or by their magnitudes, you get a new orthonormal basis given by the Q's that you've derived. Okay, and then this is just summarizing everything that I just said. I want to make sure I have enough time to go through the next example, so I'm just going to move on to the next example. And so this is, if you understand how to do this example, you'll be in pretty good shape. There isn't a lot of ways I can trick you on this. It's just a matter of whether or not you know how to do the computation. There aren't going to be like any particular hurdles that show up. And so for this example, it wants you to construct an orthonormal basis using the Gram-Schmidt process, given the independent non-orthogonal vectors v1, v2, and v3 below. So I give you 3 vectors. They're independent to one another. And I want you to form a basis or an orthonormal basis from the 3 vectors. And so you just follow this algorithm that they've detailed. So the first step is you just let E1 be equal to V1. So whatever the first vector is, you let it be equal to E1. So E1 is this equal to V1, where V1 is given by 1 minus 1, 0. So that's the first step. The second step is we need to find what E2 is going to be. And so E2, again, you can either look at, I write it out explicitly here, but it's really just this formula where J is equal to 2. So you don't really need to write out this step. And so from what I have written, it's going to be E2 is equal to V2 minus E1 transposed times V2 divided by E1 transposed times E1. And then, so this is going to give you a number, and then you multiply the vector E1 by whatever this number ends up being equal to. So as long as you know the formula, there isn't anything here that's unknown. We know what E1 is, and we know what V2 is, right? It's just a matter of plugging things in correctly and then making sure you do the computation right. So maybe it seems like a lot, but it's a lot of steps, but the steps individually aren't so bad. So this is 2. So V2 is equal to 2, 0, minus 2. E1 transposed, E1 was the vector 1, minus 1, 0. So E1 transpose is going to be 1, minus 1, 0. And then it's being multiplied to V2, which is 2, 0, 2. So I'm really just saying find the dot product between E1 and V2. And then you divide really by what's going to be the magnitude of E1 squared, but I'm just going to write it as E1 transposed times E1. And then this is all being multiplied to E1, which was equal to 1 minus 1, 0. So it's just a matter of doing this computation. And so this is going to be equal. So you have 2, 0, minus 2. If you perform this product here, you're going to have 1 times 2, and then minus 1 times 0, and then 0 times 2. So that's just going to give you a 2. Oh yeah, like this part here. Yeah, that should be a minus 2. Good catch. And then in the denominator, you have 1 times 1, and then you have minus 1 times minus 1. So it's going to give you 2, like 1 plus 1 is going to be 2. And then that's 1 minus 1, 0. And so it's really just going to be V2 minus what we had. Like this is just going to be 1, so you just subtract it. And so this is going to be equal to 1, 1, and then it's going to be minus 2. And so this is our E2. It's this vector here. And you can also check, so we should have that E1 and E2 are going to be orthogonal to one another. And so you can check and see that this is actually going to be the case. If you did E1 transpose times E2, this is the same thing as E1 dotted with E2. This would be 1 minus 1, 0 times 1, 1 minus 2. This is just going to be 1 minus 1, which is equal to 0. So that means they're orthogonal to one another. Right, and we should see, I mean, this is just how we define things. We ensure that they were going to be orthogonal from this picture. Any questions so far about finding E2? Yeah, and so the further or the deeper you go in, the worse it gets. And that when we find E3 now, it's really the same thing, except now you have to do an additional computation. So you have E3. Again, this is going to be equal to V3 minus pretty much the same formula over again, except V2 is replaced by V3. And that should be a T. It kind of look like a 2, but it should be the transpose and then do E1 transpose times E1. And then this is times E1. And then you have to add this additional part. It's pretty much the exact same formula, except wherever you see a 1, you replace it with a 2 instead. So this is going to be E2 transposed times E3. And then it's going to be E2 transpose times E2. And then all multiplied via E2 or 2E2. So you have V3 minus something times E1 minus something times E2. That's what's going on. It's kind of like a simultaneous error that's occurring. That's a little bit difficult to draw. And so if you plug everything in, I'm going to show you what it looks like, and then I'll just tell you what the answer ends up being. So this is V3 was the vector 3 minus 3, 3. That 3 is really ugly. So this is minus 3, 3. And then this part right here, pretty much exactly what we had written above, except instead of V2, we have V3 instead. So this is going to be minus 1, minus 1, 0. Dotted or times V3. So it's going to be 3 minus 3, 3. We've already, so this E1 transpose times E1, we already computed this in the first part. We found that it ended up being equal to 2. So I'm just going to write out 2 down here. And then this was times E1, where E1 is 1, minus 1, 0. And then you have to do another subtraction. So you do E2 transposed times V3. You found E2 was this vector, 1, 1, minus 2. So this is going to be minus 1, 1, minus 2 times V3, which was this 3 minus 3, 3. And then you divide really by the dot product of V2 with itself. It's going to be 1 squared plus 1 squared plus minus 2 squared, which is going to be 6. So I'm just going to write 6 here. And then you multiply by V2 or E2, which was 1, 1 minus 2. Right, so you go through with these computations. I'm just going to kind of skip ahead and say what this ends up being. The computations themselves aren't bad. It's just a couple of dot products. Will give you scalars that you then multiply to these vectors, and then you take this and subtract by these two vectors. And what you'll end up getting is that this is going to be the vector 1, 1, 1 by the end of it. And you can check and make sure that E3 actually ends up being orthogonal to E1 and E2 via the dot product. And so this is the orthogonal basis that we found. So there's still one more part, but the other part is kind of the easy part. So this is the orthogonal basis. So for the orthogonal basis, we had E1 was equal to 1 minus 1, 0. We had E2 was equal to 1, 1 minus 2. And then we had that E3 was equal to 1, 1, 1. Right, so we're just using this formula over and over again. That's really the first half of the Gram-Schmidt method. Or maybe I should say the first 75%, because this last part's pretty easy. Any questions about finding E1, E2, and E3 at all? Yeah.
Since you check, even if E3 is correct, you do E1 transpose, then you do with E2 transpose.
Yeah. Or you can just think in terms of dot products. Yeah. Either way. Yeah, so I'm going to quickly go through the last part so that way we have more time on the quiz. So the last part is just taking these vectors and transforming them into unit vectors. And so to actually get the unit vectors or the orthonormal vectors, so to find the orthonormal vectors, you just take each of these vectors and divide by the magnitude. So you have like Q1 is equal to E1 divided by the magnitude of E1. So this is going to be equal. So the magnitude of E1 is going to be the square root of 1 squared plus minus 1 squared. That's just going to give you the square root of 2. So it's going to be, I'm going to write it like this. It's 1 over the square root of 2, and then you have 1 minus 1, 0. So that's your Q1. Q2, I mean, at this point, it's not really that different. It's just E2 divided by the magnitude of E2. If you do the magnitude of E2, it's going to be the square root of 1 squared plus 1 squared plus 4 or plus 2 squared, which is going to give you the square root of 6. So this is 1 over the square root of 6, and then you have 1 minus 2. And then for Q3, the final vector, again, it's going to be E3 divided by the magnitude of E3. And so the magnitude of E3 is just the square root of 1 squared plus 1 squared plus 1 squared. It's going to give you a square root of 3. So it's going to be 1 over the square root of 3, and then you have the vector 1, 1. Right, so you can see the hard part is constructing the orthogonal basis. Finding the unit vectors isn't so bad. You just divide by what the magnitudes are. So the orthogonal part is the interesting part. Any questions about this example at all? Yeah, so we'll see other examples in the future, but this is something you need to know how to do, not just for the exam, but in like chapter 6, we're going to be doing a lot of stuff with the Gram-Schmidt method as well. Any questions? Okay, yeah, so I'll pass out the quiz. I also have, I graded the exams over